start again. Next speaker is Marco Zaninelli, who will speak about the Pythagoras number of the function field with one variable.
Okay, I would like to thank the organizer for letting me speak. And yes, I would like to talk about the Pythagoras number of a function with one variable. So the Pythagoras number is usually the number of squares that are necessary to write any sum of squares in a field as sum of that many squares. I will need some notation. So first I will fix a field K, and I will use K for the whole talk. I will need a notation for the sums of n squares in the field. So this. I will need a notation for all the sums of squares in the field. I will denote them by sk. And I will denote the Pythagoras number. Yeah, we'll define it in this way. So the smallest integer, such that any sum of squares in K is a sum of n squares in K. And if such integer doesn't exist, we decide that the Pythagoras number is infinity. Okay, so let's see a couple of examples. So let's think, for example, about our favorite fields, the real numbers. So in the real numbers, any sum of squares is positive, so we can take the square root, which means that the Pythagoras number of the real numbers is 1, right? Needless to say, we can do the same, kind of the same argument for C, easier. So the complex numbers also have Pythagoras number 1. What's our third best favorite field? The rational numbers, right? So you might have heard yesterday during the problem session, you might have heard about the Lagrange's 4 squares theorem, which is actually for the integers. So it says that any positive integer is a sum of 4 squares of integers. So from this, it follows that the Pythagoras number of Q is 4. Let me mention actually that proving it for Z is more difficult than for Q. So for Q, it was done already by Euler by using his 4 squares identity. But it doesn't matter. So the fact is that any positive rational number can be written as a sum of 4 squares of rational numbers. So, okay, let's say that these are our favorite fields, but I would like to talk about function fields. So what's the simplest example of a function field? The rational function field, one variable, right? So I would like to know what the Pythagoras number of this field is. So it's not too difficult to show that this is 2. So just taking polynomials, looking at the roots and the complex numbers, it's really not difficult. And for the complex numbers, this is also 2. Also not too difficult. Let's see, for the rational function field in variable over Q, this is actually much more difficult. So this turns out to be 5, but it was proven by Couchet in 1971, and the proof is quite long and very technical. And so he's using a local principle, approximation, density. It's really a convoluted argument. So already computing the Pythagoras number for such a relatively standard field is quite complicated. Now from these examples, you might wonder, okay, does the Pythagoras number grow of 1 when we add one variable? So question, does pkx equal pk plus 1? And the answer is no, very no. So actually, none of the two inequalities, so bigger or equal or smaller or equal, holds. However, the bigger or equal inequality holds if we restrict to nice fields, so or a certain kind of fields, namely the real ones. So let me introduce the level of a field. So we denote the level of a field with sk from the German word for level, and we define it as the minimum integer such that -1 is the sum of n squares. So again, there is no reason why this should happen. Think about the real numbers, I don't know. So if this set is empty, we just define the level as infinity. So this is called the level. So in this case, we say that k is non-real. So if -1 is the sum of squares, we say that k is non-real, and otherwise we say that k is real. So as I was saying, one of these two inequalities is related to the level. So let's say facts. If k is real, and we actually do have that the Pythagoras number of kx grows of at least 1. If instead k is non-real, we still have a relationship. There is still a relation between sk, between the level and the Pythagoras number. So of course, the Pythagoras number is bigger or equal than the level, that's by definition. But it's also easy to see that the Pythagoras number is smaller or equal than the level plus 1. So in this case, there is not much space for the Pythagoras number. Other curious fact due to Pfister is that the level is always either infinite or a power of 2. So this means that if -1 is a sum of 7 squares in a field, then it's actually a sum of 4 squares. Or if it's a sum of 15 squares, then it's a sum of 8 squares. But good, I will mostly focus on function fields and not real fields. So I was saying, if the field is real, then this inequality holds. But fine, can it be very big? Can it be bounded by some other formula? And the fact is, we don't know it. So computing the Pythagoras number becomes so complicated that we don't even know. Open problem. We don't even know if the finiteness of the Pythagoras number of the base field implies the finiteness of the Pythagoras number of the rational function field in one variable. So you can see that I would like to talk about the Pythagoras number of arbitrary function fields. Yeah, I won't give a bound for arbitrary base fields, but I would like to give you some way to compute an upper bound for the Pythagoras number of function fields over a certain base field, or let's say a family of base field, which is well behaved somehow. So yeah.
Do you have an explicit example where the equality is stripped?
Where?
An explicit example where the equality is stripped?
Yeah, for example, the standard example is the Pythagorean closure of Q. So basically, it's the smallest field with Pythagoras number 1 containing Q. So this is, of course, Pythagorean, but if we add one variable, then this is at least 3. Actually, it's either 3 or 4. I think in Pfister's book about quadratic forms, he writes it's 3, but it's a mistake. We don't know if it's 3 or 4. So there is no easy formula like we add the variable, then it's smaller than twice the Pythagoras number of the base field. No, we don't have it. Okay. What was I saying? Yeah, so I would like to give you upper bounds for the Pythagoras number of function fields over a certain base field. So okay, so let me give you a little more notation. So we'll find. Okay, let me first say a function by a function field. In one variable, which I will abbreviate by f1f, 1v. I mean a finitely generated field extension of transcendence degree 1, so nothing too exotic. And I will introduce a notation for this, for the biggest Pythagoras number of a function field over K. Am I writing big enough? No. Okay, please tell me if my writing shrinks. So question that I would like to tackle during this talk is, can we find an upper bound for p tilde of k for some k? So let me tell you what is already known. So this p tilde, it's a notation that we are using, but it's not in the literature. But the problem has been solved for a couple of fields. So, okay, first of all, as I was saying, for the non-real fields, the problem is not so interesting in the sense that this p tilde will easily be shown to be the level +1. More interesting is for our favorite fields. So the real numbers, and the real numbers have p tilde 2. This is complicated to prove. This was proven by Witt in 1934. Good. For Q it's even more complicated. So we don't even know exactly what it is, but we know that it is at most 6 and at least 4. So this was proven by Pop in 1991, but it hasn't been published yet. But okay, we went through his proof and it's correct. So let me say Pop is applying a local global principle due to Kato. It for functional fields over global fields. And I think you already in that paper, in the appendix of the paper, Quevelet showed that P tilde is at most 7. So Pop managed to obtain a better bound, 6. But we still don't know if it's 5 or 6. We don't know a single field, functional field in one variable over Q of Pythagoras number 6. So actually it's conjecture that it is 5. Last thing that is known, or that I would like to report here, is the P tilde of the field of formal power series of one variable over the real numbers. So this is known to be 3, and it has been proven by Becher, Rim, and Van Keel in 2014. So they applied another local principle due to Koyotelem, Parimala, and Suresh, which is based on field patching and modern techniques. So the P tilde of this field is exactly 3. Now you might have noticed that I mentioned a couple of times local global principles. So one of the typical instruments which we will use for in this context are valuation theory. And you might notice that this is a discretely valued field with residue field R. And you see immediately that this P tilde doesn't behave too well for valuations. So let me make it more specific. I will fix a valuation V on K, and I will denote by KV its residue field. So it's not too difficult to show that P tilde of K is bigger or equal than P kappa V of the residue field, but equality doesn't hold. Even when the valuation is very nice, like in this case, it's kind of the best valuation that we can have, but equality doesn't hold. So again, we don't know exactly how to relate these two things. But this phenomenon also happens for Pythagoras number. So it's also true that the Pythagoras number of field has Pythagoras number, at least the Pythagoras number of the residue field, but not. And why am I mentioning this? Because this was noticed, of course, by these authors in this paper, and they kind of find a way out of this problem, which was twisting a bit the Pythagoras number. So they defined another field invariant called P prime, which is nothing else than the Pythagoras number when K is real, and the level plus 1 if the rise. So if K is not real. So they notice that the problematic situation is given by the non-real fields. So they introduce this thing, and so they show that okay, this we already know. If V is Henselian, our evaluation is Henselian, then we already have an equality. So P prime of K is the P prime of the residue field. And so what I would like to say today, what I would like to show you today is that if you twist the whole P tilde using this kind of idea, then we do get an equality of the P tildes prime. So let's make it more clear. Ignition. So we define a P tilde prime of a field as the maximum of the P prime of a function field over K. And we are going to show that for a Henselian evaluation, B, and then P prime tilde of K is equal to.
To say something silly, but I'm not sure I understand. So, that's P. Okay, so P of R double bracket T is actually 1. That's what
Yes.
saying.
So
Okay.
the fact that maybe I should have. So the fact is that P R double parenthesis T is 1 indeed.
Yeah.
Just by the Hensel lemma. But the problem is that when we have a non-real field like C, then this doesn't work. So here we have the Pythagoras number is 2, whereas the residue field has Pythagoras number 1. So this creates kind of a jump in the Pythagoras number when we move between a field and its residue field, a valid field and its residue field. So, so that's why they introduced this P prime. And that's why now we are introducing this P prime tilde. So let me say P prime tilde is like a coherent notation with the fact that I'm using the P prime, but you shouldn't see any immediate bound. So it doesn't say anything direct. So it's difficult to show that P prime tilde behaves well with respect to Henselian evaluation and residue fields. So okay, let me give you a couple of remarks again. So P prime tilde of a non-real field is again, let's say, then P prime tilde is equal to the P tilde, which is the level plus 1. It's really easy to see. If K is real, then the P prime tilde is at least 3. So you can see, for example, this will be bigger. P prime tilde will be bigger than P tilde of R. And this is related, this is kind of the reason why this will be 3 and not 2. Maybe I should mention a couple more things. Yeah, so in general, of course, I twisted my Pythagoras number only of at most 1. So you can see that in the non-real case, the Pythagoras number is bounded by the level plus 1. So there's only one possible step of possible difference. So of course, we will inherit an inequality of this kind. Last thing that is worth to mention, it's easy to show that if -1 is not a square, so if the level of the field is not 1, then the Pythagoras number, no, the P prime tilde of K is not a power of 2. It's just a little complication. Okay, let me
Is a little bigger?
Yeah, sorry.
Okay.
So let me come to the main result I would like to explain today. So this has also not been published yet because one of the 5 authors is too busy. It's not me. But let's say that. So again, P prime tilde in general is bigger or equal than the P prime tilde of a residue field. But if V is Henselian, then we really have an equality. So you can see we cannot use directly the P tilde of the residue field in order to bind the P tilde of K, but we can use the P prime and then use this bound. Before giving you a sketch of the proof, I would like to show you how this helps us to compute practically the Pythagoras number of some fields. So let's say that these fields will be the hereditary Pythagorean fields. So define them. Okay, a field K is Pythagorean if it has Pythagoras number 1. And we say instead of this hereditarily Pythagorean if it is real and every finite real extension, field extension, of course, of K is again Pythagorean. So examples, okay, of course, R and C are Pythagorean fields. As I mentioned here, the form of our series in one variable are also a Pythagorean field. But actually, R and R double parenthesis T are also examples of hereditary Pythagorean fields. So you can see, you might know that any finite extension of R double parenthesis T is isomorphic to another form of our series over finite extension of the base field, but you know, R doesn't have many finite extensions. So yeah, those are examples of these kind of fields, and I will give one more example maybe in the problem session later. No. So yeah, I will show you now how to compute a bound, an upper bound for the Pythagoras number of function fields over hereditary Pythagorean fields. So theorem 2, or corollary of theorem 1 if you want. If K is hereditary Pythagorean, then our P tilde prime of K is either 3 or 5. So as a direct consequence, our P tilde will be at most 5. Okay. Let me sketch you the proof. So hereditary Pythagorean fields have been studied by Becker and Brucker in the 70s. And in particular, Brucker shown that K is hereditarily Pythagorean if and only if there exists a Henselian valuation V on K such that the residue field is again hereditary Pythagorean and has at most two orderings. So in line of principle, this not just in line of principle, this evaluation can also be the trivial one. So for example, think about the real numbers, then they will have the this valuation coming from the theorem will be the trivial evaluation. But good. So now the fact is that we can study KV a bit better than K, in the sense that we know that it has at most two orderings, and this is enough to bound the cohomological two dimensions. So if we say theta of K as let me just write it directly this way. So if we take the nth power of the width ring of this field, zero, I guess. So we can show that since the residue field has at most two orderings, sorry, I wanted. Okay, it's maybe it wasn't such a good idea to write it directly in this way, but the fact is that this V tilde is of KV 1 will be at most 1 because of this condition. It's some work, but it's not okay. It's not easy, but it's standard enough, let's say. So we can apply a result by L1 and LAM, saying that for any f over function field over our residue field, the Pythagoras number of f will be at most 2 to this bound plus the transcendence degree of f over k, so 1. So this is at most 4, right? Or if you prefer, with our notation, this means that the p tilde is at most 4, right? But we know that p tilde and p prime are connected. So this implies that p prime of tilde of k, this is wrong. This should be the residue field, right? Yeah. So if the p tilde is at most 4, then the p prime tilde is at most 5. And now with the theorem 1, we can lift the p prime tilde. So, by theorem 1, p prime tilde of k is equal to the p prime tilde of kv. So this is at most 5. I mentioned before that it cannot be 4 because 4 is power of 2, and moreover for a real field this is at most 3, at least 3. So it can only be p prime can only be 3 and 5, and as a consequence we get that p tilde f is at most 5. Okay, so you can see that we couldn't say anything directly on the p tilde because we cannot lift the p tilde, but we can lift the p prime tilde. Okay. Good. So that's how we obtain the bound for the Pythagoras number of functional fields over hereditary Pythagorean fields. Let me mention that, okay, we are happy to have found at most 5, but we actually suspect it should be 3. So the conjecture p prime tilde of k is 3 for any k hereditary Pythagorean. So indeed, you can see the examples I gave you of hereditary Pythagorean fields have even 2 and 3. So yeah, we conjecture that actually there is still space for an improvement. Good. Let me sketch you the proof of theorem 1 in the last 5 minutes, or maybe 10. Yeah. So is theorem 1 still on the blackboard? Yeah. So okay, this part is not too difficult and actually was already shown in by Becker, Hillman, and Kehl in 2014. So let me focus on this part. So we consider evaluation V, hence V evaluation V. Okay. And we would basically like to show that P prime tilde of KV of the residue field is bigger or equal than P prime tilde of K. So for who's familiar with valuation theory, you know that we can define the rank of a valuation. So one can define it as the number of convex subgroups of the value group, or as a dimension of the valuation ring associated to it. So the first step is reducing to evaluation of finite rank. Okay, sorry, let me first say, first of all, we reduce to the case where K is real. This is easy. Second, we reduce to the case where the valuation has finite rank. So this is done in a standard enough way. So one has to pick a subfield which is finitely generated. So one chooses it being a bit careful, and then takes uses the axiom of choice to produce a maximal unramified extension of that field, and then show that that's has same residue and behaves well. So this is relatively standard. Then one reduces from finite rank to rank 1 by induction, basically. Now one is left with a Henselian valuation of rank 1, but we still need to do one more reduction step. So we reduce to the case where V is not just Henselian of rank 1, but complete of rank 1. So this is also standard enough apparently, but it's quite work, and it involves some existentially closed definitions of which I'm not really an expert. So let me finally show you the core of the proof, which is basically which is the case where V is a complete valuation of rank 1. So one takes a function field f over k, such that p tilde of p tilde prime of k is equal to the p prime of f. Let me call this p for brevity. Good. We define a quadratic form in the following way. So we take sums of p squares, so over f. I'm defining a quadratic form over f. So I just take the sum of p squares if k is real, and otherwise I define the sums of p minus 1 square, and then I subtract a term which is given by minus a for some a in which is let's say a non-zero sum of squares in f, but that is not a sum of p minus 1 squares. So I'm choosing this element in order to make this anisotropic. Also, the existence of this is given by the fact that if k is if f is real, then the p prime, so our p, is nothing but the Pythagoras number of f. So we have such an element. But the fact is that this equality implies that phi is anisotropic, where f good. And now what do? We apply a local global principle. So there's a recent local global principle due to Flair and Nemeti, which works for, let's say, okay, she writes it in the full generality, but what we are applying here is our local global principle for function fields over completely valued field of rank 1 for quadratic forms over these fields. So basically we apply a local global principle and we find a valuation W. Okay, I promised to myself not to write the rank, but I see that now it's too late. So, now it's late. So evaluation of rank 1 is nothing but evaluation from K to a subgroup of R. So subgroup as an order, subgroup with respect to the standard ordering of real numbers. So what Nemeti's local principle will produce is a valuation of rank 1 again, so into the real numbers, but on F, and such that the restriction of V to base field is either V or the trivial valuation, and such that phi remains anisotropic over the completion of F at this valuation. So good. So you know that complete discrete value field of rank 1 is also Euclidean. So this is the case, right? So we have that the P prime tilde of Fv will be equal to the P prime tilde of the residue field. Actually, this is true this is what we want to show, but what has been shown by now is actually that the P prime of this field, these two fields coincide. And the fact that this is anisotropic implies that the P prime of the completion of F at P is bigger or equal than P. So basically this quadratic form rewrites the inequality P prime of F bigger or equal than P in terms of quadratic forms, okay? And we want to use it in both ways, let's say. So first we show that the quadratic form is anisotropic over F, and then we say, okay, but once we obtain that it's anisotropic over Fw, then we also conclude that the P prime of Fw is bigger or equal than our P. So we have this inequality, right? But now by definition, P prime of, okay, sorry. Now we observe that this, if W was trivial over K, then the residue field would be a finite extension of K, but K was taken to be hereditary, no. Okay, so there's nothing particularly deep, exclude the case that V restricted to K was 0, and conclude so we conclude that the extension of the residue field of W over the residue field of V is a function field or variable. And now by definition, the P prime tilde of KV will be bigger or equal to the P prime of the residue field of W. And we have shown that this is bigger or equal than P, which was by definition our P tilde of K. Good, so we have shown the inclusion. I canceled the theorem. I wanted to show that if V is Henselian, that P prime tilde of K coincides with the one of the residue field. Right, and the inclusion bigger or equal was known, so we obtained the other one, so we obtained the equality, right? Good. Let me mention that with this statement, we can also obtain bounds over other, not only over hereditarily Pythagorean fields, but also for other fields. For example, can you think about the field F with a Henselian valuation? Henselian valuation V such that KV is isomorphic to Q or to a number field. Then we can lift Pop's result to the field F, right? So we had Pop showed this thing. Actually, it's not too difficult to show that in this case coincides with the P prime. So you can see that by theorem 1, we obtain that P prime of F is of 6, right? So one example could be the I don't know, the initialization of Qx with respect to the x-side evaluation or something like that, right? We could also take Q double parenthesis. Let's go with T. Could also take this field, but for this field, it follows directly from the local global principle of Coyote, Parimal, and Suresh, because this is complete and discrete, not just Henselian. Good. So I think I will leave some time for questions.
Is there questions?
Yes, what happens if in the definition of hereditary Pythagorean we only consider finite extensions of 2 power order? So will theorem 2 hold?
Yeah, that's a good question, which is so you would like to know whether we can obtain the bound free for degree 2 extensions. No, we can do it for a function field of conics. The next step, which I'm planning to ask a bit in the next problem session, is for elliptic curves, function fields of elliptic curves, right? In general, I will explain it better later, but one can see that the elements which are not sums of 2 squares, which are sums of squares, not sums of 2 squares, are controlled by the relative Brauer group, the Brauer group of the curve. So it's actually more related to Brauer groups than it might look. But no, we don't know it even for finite extensions of degree 2 over.
And if K is Euclidean, do you know the conjecture?
Yeah, so okay, here I was a bit quick, maybe even more than necessary, but if K is Euclidean and hereditary Pythagorean, then it's hereditary Euclidean.
I'm asking about the conjecture.
Yeah, I'm answering about the conjecture. So if K is hereditary Pythagorean and Euclidean, then it's hereditary Euclidean. So the dimension here is the cohomological 2 dimension here is 0, and we obtain 2. So we obtain a bound 3 instead of 2. So this was actually what we found at the beginning, and then they also generalize. So yes, we know that if K is a Euclidean, yes, then it's so it's the case, for example, of K. No, it's not here anymore. So, for example, for the real numbers, the P prime is 3, right? Okay, let me say even more. Actually, field is hereditary Euclidean if and only if the P tilde of that field is 2. So,
perhaps we switch to another question.
About beings, skew mime over skew field.
yeah, give me a second.
For example, what happens with realization problem? Which numbers could be realized as a level of skew field?
Okay, that's
Any results in this flavor?
yeah. I haven't worked much on rings, I must say, but yeah, they don't behave so well, I'm afraid. I don't think you can only get powers of 2 or infinity. I think you can get other things as well.
But it looks like there are S.
It looks like
there are gaps in the values of.
Exactly. For fields, there are many gaps, like big gaps also.
Would be interesting.
I think it has been studied. I think one can check in Fischer's book. Probably he says things about. I'm pretty sure that there is some literature about levels of rings, not just of. But I'm not sure now. I think.
Okay, any more questions?
Yeah.
So this is a quite a question, but so the P test give you bounds on the Pythagoras numbers of your function fields. But if you want to look at the Pythagoras number of a given function field, is there a way, in some cases, at least in some easy cases, to relate it to the geometry of the curve you're looking at?
Yes. Yes, the answer is yes. So, for example, let me say I talked about the Pythagoras number of Q. I didn't talk about the Pythagoras number of a number field, but there is an explicit way to check at to compute the Pythagoras number of a given number field, and this consists in, there's basically Hasse-Locker-Global principle, and so the Pythagoras number will be 3 unless there is unless there is a two-adic place of odd degree, but okay, now I see that I'm with finite extension, I'm losing the curves, the geometry. But yes, one takes, for example, fields given by a function field over this kind of fields. Then yes, one can produce exactly which points of the curve give a residue field which will produce your Pythagoras number 3 instead of 2. Let's say maybe I can make an example. So for a curve, for this curve, which is called Tikhonov curve, over this field, then there is only one valuation, which is the Gauss extension along X, I think. Okay, I don't remember now if it's along X or X divided by T, but of the t-adic valuation on of this valuation is the unique valuation of function field of this curve with residue field of level of, let's say, of p prime equal to 3. So this, okay, now I'm saying this is the Gauss extension, but actually it comes from this term. So there is a way to associate, for example, in the case of hyperelliptic curves, to associate to any non-split term, so any factor of degree 2 evaluation, or a point on a curve if you prefer, which produces, let's say, a residue field or a completion also. And these things are the ones that make the Pythagoras, the p prime of the field, the Pythagoras number of the field to be 2 or 3. Yeah. Okay, I'm not sure I explained it too well, but there is a connection. Yeah.
Okay, thank you. So if there are no more questions.